This is Algebra 2, Lesson 6-4, Rational Exponents. A rational exponent is another way to write a radical expression. For example, if a to the x is equal to the fourth root of a to the third, then by definition, a to the x times a to the x times a to the x times a to the x would equal a to the third by adding your exponents. Which would be a to the 4x equals a to the third, so therefore 4x equals 3, so x equals 3/4. So this suggests an alternative notation for radical expressions in which, for example, the fourth root of a to the third is the same thing as saying a to the 4th power. Okay? You can write a radical expression in an equivalent form using a fractional, otherwise known as rational exponent of a radical sign. In general, the nth root of x is equal to x to the 1 over n for any positive integer n. Any positive integers are non-negative integers. Like the radical form, the exponent form indicates the principal root, so we'll be looking for the positive square roots. Okay? So let's take a look at this. So the square root of 25 is the same thing as saying 25 to the 1/2 power. The cube root of 27 is the same thing as saying 27 to the 1/3 power. And the fourth root of 64 is saying 64 to the 1/4 power. Notice the index, okay, becomes the denominator of your fraction every single time. The index becomes your denominator. My index here was 3, my denominator was 3. My index was 4, my denominator was 4. Okay? So, you can use that knowledge to simplify expressions. Okay? For example, we're going to take and simplify 625 to the 1/4 power. Okay? Which basically means the fourth root of 625, doesn't it? It means the fourth root of 625. And if you know anything about fourth roots, I know that this is the perfect fourth root, right? Because it's 5 times 125, which is 5 times 25, which is 5 times 5. So the fourth root, 625 to the 1/4 is 5. Okay? The 12 to the 1/2 times 12 to the 1/2, remember, these have the same, okay, it's just like saying a to the second times a to the third. That would become to a to the 2 plus 3. I'm going to do the same thing here. This is 12 to the 1/2 plus 1/2, which becomes 12 to the 1st power, which is just power. Okay. The 12 to the 1/3 times 18 to the 1/3 is the cube root of 12. Okay. That's the cube root of 12 times 18, right? And 12 is 2 times 6, 6 is 2 times 3, 18 is 3 times 6, and 6 is 2 times 3. So if we pair things up, we have groups of 3. Okay, we have one group of 2s, and we have one group of 3s, and 3 times 2 is 6. Okay. Nice little way of dealing with exponents. Now, so if the nth root of x equals x to the 1 over n, it follows from our law of exponents for all real numbers that the nth root of x to the m is the same thing as saying x to the m to the 1 over n power, which is quantity x to the 1n to the nth power, which is the same thing as saying x, the nth root of x to the m. So notice it doesn't matter where this number is. Okay? It can be inside or outside the parentheses, what it's trying to tell you. Okay, this leads to the definition of a rational exponent. If the nth root of a is a real number, and m is an integer, and m divided by n is in its lowest terms, then a to the 1 over n is equal to the nth root of a, and a to the m over n is equal to the nth root of a to the m, which is the same as the quantity of the nth root of a to the mth power. And that only works, okay, if m is negative, then and a does not equal 0. Okay. All right. That may be a little confusing, but once we work on some problems, it'll be a lot less confusing. So if you're going to convert between exponential and radical form, so if we have something written with exponents and we want to write it as a radical, remember the denominator becomes your index number. Okay, so whatever's on the bottom becomes your index number. So this becomes the 7th root of x squared. Here we're going to have the 4th root of 7xy all to the 5th power. If all we're doing is writing this in exponential form, writing it from exponential form to radical form, we don't need to simplify it. It just said to write it in radical form. It didn't say write in radical form and simplify. It just said write in radical form, so we can stop at that point in time. Okay? Letter C is the 6 to the 7/5, which means the 5th root of 6 to the 7th power. Right? And it could be written that way, or it could be written this way. Means the same thing. That's what that little box above said. It doesn't matter where you put that 7, if it's inside or outside, it's still the same thing. Now, we have them in radical form now, and we're going to write them in exponential form. Right? So if I have the cube root of 11, that's the same thing as saying the cube root of 11 to the first power. Remember, if there's no index number there, it means 1. So this becomes 11 to the 1/3 power. Here we have 3x, and since the 3 and the x are both in parentheses, it needs to stay in parentheses to the 1/5 power. If just the 3 was in parentheses, then it would be 3 to the 1/5. Okay, you got to make sure you pay attention to those little parenthesis things because they do mean. Okay? By the way, we could rewrite this as 3 to the 1/5 x to the 1/5. Okay, the parentheses mean something, so make sure you pay attention to it. Because if it was okay, for example, if this was the 5th root of 3x squared y, then the square is only going to apply to the 3x. That's why the parentheses mean something. It doesn't apply to the y. That's why I said pay attention to where your parentheses are. In this particular instance, we didn't change our problem with letter B, but it would if you did the alternative. Let's look at letter C now. This is just an example. Okay. The 4th root of a to the 3rd b squared c. Okay. That means this is a to the 3rd b squared c all to the 1/4 power. Okay. I personally like to simplify this a little bit better by distributing this 1/4 through. So I would make this a to the 3/4, b to the 2/4, which is 1/2, c to the 1/4. Okay. Either way works, because if you're just writing in exponential form, right, either form works. A to the 3/4, b to the 1/2, c to the 1/4, or you can have it a to the 3rd b squared c all to the 1/4 power. They both mean exactly the same thing. It's important that you understand that they both mean exactly the same thing. All right, using rational exponents. Okay, we'll do a little physics here. Kepler's 3rd law of orbital motion states that you can approximate the period p in Earth years it takes a planet to complete one orbit of the sun using the function p equals d to the 3/2, where d is the distance in astronomical units, AU, from the planet to the sun. We're going to find the approximate length in Earth years of a Venetian year if Venus is 0.72 astronomical units from the sun. And you might have been lost in the problem, but just look at what it's asking. It's asking us to find the approximate length in Earth years, and that's with using this function right here. So p equals d to the 3/2. Okay. Now it says find the approximate length if Venus is 0.72 astronomical units from the sun. So we're looking for the period, so we're looking for p. So p equals, our distance from the sun is 0.72 to the 3/2. And since it said approximate length, we actually put that in the lovely calculator, and your calculators can do an exponent to a fraction. Both the calculators can. Right? You're just going to put in 0.72, make sure it's in parentheses, take it to the 3/2 power. Okay? You might need to put the 3/2, if you're using the 84, you might need to take this and put it in parentheses. If you're using the Inspire, just use your fractional exponent key, and you don't have to worry about the parentheses. Now, if I stick this in, my period is approximately equal to 0.6109. So the length of a Venetian year is about 0.61 Earth years. It's a word problem, so you should answer the complete sentence. There we go. at some properties of rational exponents. And these follow along with the properties of regular exponents. Okay, they actually are exactly like the properties of exponents, but now we're just going to add the word rational to it. So the original property says, we had the property that says a to the m times a to the n is a to the m plus n. So when you have rational exponents, you're still going to add your exponents. So 8 to the 1/3 times 8 to the 2/3 is the same as 8 to the 1/3 plus 2/3, which is 8 to the 3/3 or 8 to the 1st or just 8. A power raised to a power is multiplied. A to the m raised to the nth power is a to the m times n. So if I have 5 to the 1/2 raised to the 4th power, I'm just going to multiply that exponent 1/2 times 4, and I'm going to get 5 squared, which is 25. Okay? If you have a quantity raised to a power, you have to separate it and make sure you distribute that quantity through, which is what I did in letter C of the last example before the astronomical unit, before the Kepler's law problem. Okay? So if I have 4 times 5 to the 1/2, that means that's 4 to the 1/2, 5 to the 1/2. Okay? And 4 to the 1/2 is 2. 5 to the 1/2 stays as 5 to the 1/2, so it becomes 2 times 5 to the 1/2. You can't multiply those because they're not the same units per se. And remember, if you have a negative exponent, it's the same as 1 over that exponent to the positive. So 9 to the negative 1/2 is the same thing as saying 1 over 9 to the 1/2, which is the same thing as saying 1 over the square root of 9, which is 1/3. Okay, so all of these properties are the same properties of exponents, but now we're dealing with rational exponents. Okay? Same properties you had when you took Algebra 1. They were first introduced in pre-algebra if you had a pre-algebra class, and then they were reinforced again in Algebra, Chapter 8. Okay? So these are just the properties of exponents as applied to rational numbers. Okay, now let's look at a couple of things. Remember in Lesson 6.2, we simplified products or quotients involving radical expressions only when they had the same index. However, you can combine radical expressions with different indexes if you convert them to expressions with rational exponents. Okay, so now I can find a product or quotient in the simplest form if it doesn't have the same root, because I can put it in rational exponent form. Okay. Okay, so, by the way, this is the 6th root of 10, not the 5th root of 10. So I have the 6th root of 10 times the cubed root of 10. So that becomes 10 to the 1/6 times 10 to the 1/3, correct? Remember, normally we couldn't combine these because they don't have the same index number. But if I use the properties of exponents, I can do this because I know that I'm adding my exponents. This becomes 10 to the 1/6 plus 1/3. Well, I need to get a common denominator, which becomes 10 to the 1/6 plus 2/3, and 2/6, not 2/3. So that ends up to be 10 to the 3/6, or 10 to the 1/2, which is just the square root of 10. Okay? So that's how you can simplify when you don't have the same index numbers, if you can use rational expressions instead of the radical expression. So if I have the square root of x to the 3rd divided by the cube root of x squared, remember, this would be x to the 3/2 divided by x to the 2/3. Right? Which means that when you're dividing, you actually subtract the exponents. You have x to the 3/2 minus 2/3. We have to get a common denominator, which would be 6. So that becomes x to the 9/6 minus 2, 6, 4, 6. So this would become x to the 5/6. Okay? Or the 6th root of x to the 5th. So rational exponents really allow us to do quite a few more things than radical exponents did. Okay? You may have noticed once in a while, if you're trying to check things with your TI Inspire, that it oftentimes put things in rational exponents. And I specifically didn't address that until now because I didn't want to rely on that calculator. Now, you can simplify a number with a rational exponent by using the properties of exponents or by converting the expression to a radical expression. So let's take a look at negative 32 to the 2/5. There's two different ways you can do this. I'm going to show you both ways. I don't care which way you choose to finally do it. Find one way you like really well, perfect it, and use it. Okay? Method 1 says that I'm going to take this and I'm going to change it to all rational exponents. So I have negative 32 to the 2/5. Okay? And you might say, but it's already in rational exponent form. Not really, because negative 32 is the same as saying negative 2 to the 5th. So this becomes negative 2 to the 5th power raised to a 2/5 power. A power to a power is multiplied, so this becomes negative 2 to the 5th times 2/5. Because a power to a power is multiplied. So we end up with negative 2 to the second power. Negative 2 to the second power, which is this. Method number 2 here would be saying you take negative 32 to the 2/5, and you're going to change it to radical form. So I'm going to take this as being the 5th root of negative 32 squared. Okay? So I'm going to have the 5th root of negative 32 times negative 32. Okay? Well, that's not, what am I doing? I can't do that. So I can't do, yes I can, never mind. I'm thinking of something else. Okay, so I've got negative 32. Okay? Which I know is, from over here, is 2 to the 5th, negative 2 to the 5th. Okay, so this is negative 2 to the 5th power times negative 2 to the 5th power. Okay, underneath the 5th root. Okay. Which I actually would just look at this and saying, okay, how many can I take out? That means I can take out, there's 1 I can take out, there's 2 I can take out, so I can take out 2 of those. Which still ends up pretty cool. I don't care which way you choose. Find one you like and do it. Let's do another example. Okay, because sometimes people don't get this until I do it twice. I'm going to do 4 to the negative 3.5. Okay, 4 to the negative 3.5. Not this, 3.5. Is the same thing. Remember, negative 3.5 is the same thing as negative 7.5. So, excuse me, this is like saying 4 to the negative 7/2. And 4 is 2 squared, so it's 2 squared to the negative 7/2. So that's 2 to the 2 over 1 times negative 7 over 2, because a power raised to a power is multiplied. So you end up with 2 to the negative 7, which is 1 over 2 to the 7th. 1 over 2 to the positive 7, remember that? And 2 to the 7th is 128. So you get 1 over 128. If we look at it using radicals, we have 4 to the negative 3.5, which is the same thing as saying 4 to the negative 7/2, just like we had before. Okay? Which is saying the same thing as saying 1 over 4 to the 7/2, which is 1 over the square root of 4 to the 7th power. Okay? And the square root of 4 is 2, so that's the same thing as saying 1 over 2 to the 7th power. Oops, I messed that up. This is the same thing as saying 1 over the square root of 4 is 2, 2 to the 7th power, which is the same as saying 1 over 128. You get the same answer regardless of which way you do it. I actually like using rational exponents a little bit better because I think it's a little cleaner and a little bit easier, but sometimes I go back to using radical exponents. It doesn't matter to me, whichever one you're better at, okay, is the one you probably should use. So let's actually practice that. Simplifying numbers with rational exponents. I have 16 to the 3/4. Okay? I know 16 is the same thing as saying 4 times 4, which is 2 times 2 and 2 times 2. So it's 2 to the 4th raised to the 3/4, which is the same thing as saying 2 to the 4 over 1 times 3 over 4, which is 2 to the 3rd, which is 8. I much prefer doing it with rational exponents than radical exponents because it's just faster. Okay? Now we'll take 9 to the negative 3.5. That's 9 to the negative 7 halves, which is the same thing as saying 9 is 3 squared. So 3 squared to the negative 7 halves. A power to a power is multiplied, which means this is 3 to the 2 over 1 times negative 7 over 2. Remember, these cancel. So I have 3 to the negative 7th, which is 1 over 3 to the 7th power. And if I put 3 to the 7th in my calculator, I get 1 over 2,187. Okay. I find it easier using those than it would be to take the 4th root of 16 to the 3rd power. It's just a personal preference. Now, to write an expression with rational exponents in simplest form, write every exponent as a positive number. This is very important. Every exponent, not number. I'll get some people who go, I have negative 2, so I need to put that as 1 over 2. No! Negative 2 can be negative all day long. You just can't have negative exponents. Okay, there's a huge difference here. So, let's take a look at this. So if we're going to write each expression in simplest form, we cannot have any negative exponents. So that's what we need to make sure we get rid of. So 16 is 2 to the 4th. So I have 2 to the 4th, y to the negative 8, and I'm taking all of that to the 3/4 out. Remember, I have to distribute this. So this means 2 to the 4 over 1 times 3 over 4, y to the negative 8 over 1 times 3 over 4. Okay, so these cancel, so I get 2 to the 3rd. Here, this goes into itself twice, so I have y to the negative 6th. I can't have a y to the negative 6th power. Okay. Whoops, I missed a negative. God, all the way back here, I missed my negative. It's right up there, so this should have been negative 3/4. So this would have been negative, and this would have been negative here, which changes my answer over here. Sorry about that. Careful. That's why it's really hard if you're not neat. Even with the computer, sometimes it's hard to see those negative signs. I missed that one, so I started looking a little bit further. So basically, I have 2 to the negative 3rd now, y to the positive 6th. Okay. I have a negative exponent on my 2. 2 is positive, but the exponent is negative. So this must be taken care of. It must be made into a positive exponent. So the y to the 6th stays on the top, and the 2 to the negative 3rd becomes 2 to the positive 3rd, moving to the bottom. And last but not least, we simplify that to be y to the 6th over 8. All right, let's look at number 2. Make sure I don't miss any negative signs this time. All right, so it's 243a to the negative 10, all to the 2/5 power. All right, I'm thinking 243 is divisible by 3. Let's see, let's think about this. It's 3 times 3 is 81, which is 9 times 9. This is 3 times 3, and 3 times 3. So it's 3 to the 5th. So I have 3 to the 5th, a to the negative 10, all to the positive 2/5 power. So if I distribute, I get 3 to the 5 over 1 times 2 over 5, a to the negative 10 over 1 times 2 over 5. These 5's cancel, so I get 3 squared. 5 goes into 10 twice, so I get a to the negative 4. Okay? So I have the negative exponent, so it has to move to the denominator. So I have 3 squared over a to the 4th, which becomes 9 over a to the 4th. And last but certainly not least, look, we have something on the outside, inside. We got a radical, we got all kinds of interesting stuff here. So we have 9x, 4th roots of y to the 3x. So I'm going to just change this 4th roots of y. So I'm going to have 9x, y to the 1/4, all to the 3x. Okay, I just changed that so that it's all rational exponents versus a radical exponent and a rational exponent, which can get really confusing. So 9 is the same thing as saying 3 squared. So I have 3 squared x, y to the 1/4, and I'm taking all of that to the 3/2 power. So distribute that 3/2. I'm going to start writing it in a different color so it doesn't get mixed up with my other column. I have 3 to the 2 over 1 times 3 over 2. x to the 1 over 1 times 3 over 2, and y to the 1 over 4 times 3 over 2. Okay, so if we simplify, remember these two 2's cancel out, so I've got 3 to the third, x to the 3 halves, y to the, looks like 3/8, doesn't it? Okay. Yep. That's what I have so far. Okay. I know 3 to the third is it's going to be 27, so I can do that part. So I now have 27, but I have x to the 3 halves, y to the 3/8. I can't have two different radicals in this expression if I want to simplify it. And I can't leave it with a rational exponent because that's not simplified. So what I have to do is I have to get a common denominator between 3 halves and 3/8, which would be 8. Okay, so I'm going to multiply this by 4, this by 4. So I'm going to have 27, x to the 12/8, y to the 3/8. Okay, so we have 27, x to the 8th root, okay, of x to the 12th, y to the 3rd. Right? But I can simplify that just a little bit because I can take out an x, can't I? Okay, so now I can take, remember, 12 divided by 8 is 1, remainder 4. So I can take another x out, so this becomes 27x squared, 8th roots of x to the 4th, y to the 3rd. And I'm finally done. Like, you can clearly see there are so many little places where you can make a small error, which will compound into a gigantic error. So be careful when you're dealing with rational exponents. They're not hard. You just have to remember your properties of exponents, which you learned in algebra, but they can trip you up if you make simple mistakes.